That was a wonderful introduction. There is nothing left to say. She said basically everything you need to know about me. And probably this is going to be my last science talk, because at the end of April I'll be leaving Institute for Astronomy and I'll start a new job at the National Science Foundation in the US. So this is probably my last science talk in the years to come. So anyway, it's a great pleasure to be here. Thank you very much for the invitation. And I'm really happy that there are so many young people in the audience. And over the next 45 minutes, I'll try to entertain you about the sun. I know that not many of you are experts on the sun, so I'll keep my talk at a very basic level to make sure that everyone understands what I'm talking about. Basically, what I'll try to do over the next 45 minutes is tell you the big picture. We have lots of observations, and we try to interpret those observations. We try to understand the underlying physics on the sun. And that's something that intrigued me about the sun. We have a lot of observations. This is not order of magnitude science. We're talking about really precise observations with high cadence on a very high spatial resolution. And the challenge is to understand the underlying physics. And I'll tell you what we managed to understand over the last 13 years, ever since I've been doing solar physics. And at this point, it's a good time to introduce the collaborators, people that I worked with most of the time over the last 6 years. Elena Moise, who is now at the Institute of Geodynamics, my wonderful wife, we did a wonderful paper together published recently in Nature Physics. I'll tell you about it. Cooper Downs, who is a former graduate student of mine, and he works in predictive science in San Diego. Nada Al-Haddad is also a student of mine. He is now at the University of Leuven. Noel Lugas, he used to work with me in the University of Hawaii, and he's now at the University of New Hampshire. And I have another European collaborator, Klaus Gausgaard, from Niels Bohr Institute in Copenhagen. So you see that we have collaborators from all over the world, and the kind of research that we've been doing over the last 7 years is not a single person effort. It takes multitude of efforts in order to get the kind of results that we've done. So, what is the underlying motivation for this one? What we've been trying to do over the last 7 years is build some sort of realistic tool, as realistic as it gets, in which we can simulate some phenomena that occur on the sun. And we're mostly interested in the large-scale phenomena, such as flares, extreme ultraviolet waves, coronal mass ejections, and other related phenomena. And there are a couple of teams in the US that are heavily involved in this. There is one group at the University of Michigan, and they developed this so-called space weather modeling framework, SWMF. There is another group centered at Boston University, and they have collaborators from all over the country. That is the Center for Integrated Space Weather Modeling, CISM. And one of the collaborators are people from Predictive Science Incorporated. So they developed alternative suite of models called Core Health. But during the talk, I will mostly talk about the space weather modeling framework that was developed at the University of Michigan. And the main goal is to study processes that occur on the sun all the way from the convection zone to the surface of the Earth. So it tries to cover the entire space from the surface of the sun to the surface of the Earth. They call it sun to mud simulation. So in order to build this type of realistic tool, what you need to have is you need to incorporate some real observations. And as I said, the sun is unique because we have a lot of observations, not just remote sensing observations from a great suite of satellites in various wavelengths, but also in situ observations from satellites at the first Lagrangian point and some other locations. So you need to incorporate those observations in one form or another, in the form of either boundary conditions in your model, initial conditions, and so forth. And then you need to be able to reproduce some directly observable quantities from your model. The tool that I mentioned earlier, they're based on magnetohydrodynamic approximation. So you have basic quantities that you put in your model are 3 components of the velocity, you put the proton density, you have the proton temperature, and then you have 3 components of the magnetic field, and these are the basic quantities that your model works with. But this is not what you observe. Remember, when you have satellite like SOHO, and you observe the sun in extreme ultraviolet, you have some emission measured at a given wavelength, and that's not what your model gives you. In order to compare your simulations with observations, you need to reproduce those observations. So you take those basic quantities and you calculate what will be the emission measured at a given wavelength. And then, once you have the capability to reproduce observable quantities, then you compare apples with apples. And then you can claim that your model can actually simulate the real sun. So this is really important. And when you have a model like this, then you can compare with direct simulations, with direct observations. And what are the advantages? The advantages are that now you can interpret complex observations, assuming that your model is correct, physical model is correct. And as I said, we have observations from Solar Heliospheric Observatory, we have observations from Solar Dynamic Observatory, which was launched only a few years ago. We have the two stereo satellites along the Earth orbit, and in the future we'll have Solar Orbiter, Solar Prof, so we have a lot of observations. When you compare with your model with observations, of course, they will not agree. So what you do then is go back to your model and ask yourself the question, why my model doesn't fit observations so well? So you go back to the model, you make some changes in order to get best agreement observations. And then you can claim that your model represents the actual physical picture. That's what took us a long time to validate the models, to make sure that they are correct in some steady state conditions. Because when you have some dynamic phenomena occurring on the sun, it's very difficult to validate the model. So the validation process goes in two steps. First, we compare our model for some steady state conditions on the sun and the solar wind, and then we use this validated steady state model to study dynamic phenomena. And the third very important thing about the model is you can fill data gaps. Your observations are not perfect. I don't want to insult observers, but there are always some problems with instruments. Instruments goes down, you have a data gap, an interesting phenomenon occurs on the sun, and you cannot capture some of the important part of the phenomenon. Models, they don't have data gaps. Of course, if the model blows up, if it becomes unstable, of course, we have a problem, but other than that, your model can go forward in time, it can go backward in time, and their advantage is models are much cheaper than observations. You don't need to pay billions of dollars to launch a satellite. With model, you can cover the entire three-dimensional space, assuming that it's correct, and you can provide some interpretation of observations or missing observations. So basically, this talk will talk about the tool that we developed and what kind of progress we managed to get. So the key features in our model, I will mostly talk about the sun, what happens in the upper convections on the photosphere, the corona, and the first 20 solar radii above the surface. So we developed this model of the solar corona that is based on real solar observations. We have a lot of instruments that measure the magnetic field of the sun. Problem is, just recently we began to measure the three components of the magnetic field. But most of the ground-based observatories, they provide only the line-of-sight component of the magnetic field. From there you can derive the radio component of the magnetic field, but you don't have much information about the horizontal magnetic field. And then these observations are typically at the photosphere of the sun. And you can get a map of the radio component of the magnetic field of the sun averaged over an entire solar rotation. So that's what we call some steady-state picture of the sun over an entire solar rotation. And we use that to set boundary conditions for the magnetic field at the sun. And that's the lower boundary in our model. And of course, you need to have the information about magnetic field in all three dimensions in the entire space. So what you do is you take this boundary condition for a magnetic field and you assume that the magnetic field in the solar corona is potential. So what you do is you extrapolate the field in the entire corona, assuming that it is potential. The idea is just to get the initial guess, the initial distribution of the magnetic field. And once you include the important physics that heats up the solar corona, that accelerates the solar wind, then your model will relax this initial state into some steady state, which will no longer be potential. That is the key. So the whole idea is to start the simulation with some good guess about the initial magnetic field, the initial velocities, densities, and temperature. For the velocities, it's simple. We just assume that there are no flows in the entire volume. The tricky part is to get the densities and temperatures. Remember, we have observations, but these observations, they don't tell you exactly what the density and temperatures are at a given point in space. Best you can get is, if you have some emission measure, you can get some integrated density square along the line of sight. So you have the current density of protons. But this doesn't tell you what the density is at a given point in space, because most of these observations are optically thin. So you look at observations and you try to guess what the initial temperatures and densities are. And when you look at the sun, you will notice that in regions where you have strong magnetic field, like Arctic regions, temperatures tend to be higher, densities tend to be higher. So we found a good way to prescribe the densities and temperatures by using the magnetic field as a proxy. And this took a long time to find the right functional dependence of the densities and temperatures on the magnetic field. And of course, you need to put the right physics into your model. You need to put optically thin radiation, you need to put some volumetric heating due to waves, due to dissipation of electric currents, and of course, there are some proxies for those functions. They depend on density, they depend on temperatures, magnetic field, and so forth. But the most important thing is how you drive the solar wind. You know that the sun has a solar wind that permeates the entire space, solar corona, and extends all the way to the boundaries of the solar system. So we found a very nice way to prescribe the acceleration of the solar wind, assuming that there is some turbulence presence in the solar corona and there is some energy exchange between the solar plasma and the turbulence. And I'll show you how this model basically reproduces observation. So you have this initial state, you have these important physical processes that take place in the solar corona, and then you need to advance the solution in time. So you have initial conditions, boundary conditions set up, and then you try to cover the entire space from the surface of the sun to the Earth, of course. And if you do this in 3 dimensions, you face an enormous challenge. If you use uniform grid in the entire space, then it will take enormous computational resources. So what the group at Michigan came up with, and not just this group, but other group, is use numerical tools in which you have non-uniform grids. So you put most of the computational efforts in regions of interest. For example, where flare occurs, where coronal mass ejection takes place. So you refine the grid as much as possible in that region, because that's the interesting part of the sun. And the rest is not so interesting because we have some steady-state conditions, so we don't put much of the computational efforts in that region. So you have these block adaptive meshes, and then when an event takes off, you want to keep track of the evolution of the CME, so you keep refining the grid, numerical grid, along the path of the evolution of the CME. This is again a big challenge, computational and also computer science challenge. And as I said, it took us a long time. You see, the first results were published some 10 years ago. This is a model that I developed with co-authors, and the whole idea is to reproduce the steady-state solar wind conditions. What you see here is black dots. Well, these are actually observations. They look messy. They look like real observations. And the red curve is model results. This is the solar wind speed. This is the proton density. This is the solar wind temperature. Basically, the model that we developed tries to provide the best fit for those observations. And we know that the solar wind is by model. We have 750 kilometers per second for the fast wind, and we have 450 kilometers for the solar wind, and so forth. So we designed the model. We designed the interaction between the plasma and the emission turbulence in such a way that the wind that you reproduce in a model represents this bimodal structure of the solar wind. And we tested the results with great suite of satellites. Then we validated the model using white light observations. This is the light scattered by free electrons in the solar corona. This is the photospheric light scattered by free electrons in the solar corona. And what you see here on the left-hand side, these are observations from the solar heliospheric observatory. You can see nice dense streams. Basically, the regions where you have that are brighter, they represent regions where you have high concentration of electrons, scatter more light. So these are regions where you have high density. And this is a coronal mass ejection that took place. You can see the solar disk, this is the occulting disk. And this is the model. You don't capture the details of the simulation, but what is important for us is to capture the general properties of the CME. In particular, the evolution of the shock of the CME as it travels through space. And I'll talk about the shock wave. And you can see how the resolution changes. This is, for example, the shock position here shows where the grid changes. Here the grid is twice coarser than here and so forth. So this is just to tell you that when you start the model, you have no choice but to have this block adapted grid and non-uniform meshes. And we also spent a great effort trying to simulate the extreme ultraviolet emissions. This is an early version of the model developed by my former graduate student Cooper Downs. These are actual observations from the EAT instrument on board Assoc. These are extreme ultraviolet lights at 3 different wavelengths. And this is the comparison. And these are results from the model itself. Okay. Now that you have this model that you can claim to simulate below some steady state conditions, you can utilize this model to study dynamic phenomena. And of course, of great interest for everyone is to study the larger scale phenomena that take place on the Sun, namely coronal mass ejections. These phenomena were under debate for over 40 years. They were discovered back in 1973 by Skylab, the first NASA mission, and they've been under debate for almost 4 decades now. The problem is we don't know much what is happening at the convection zone. And the convection zone is where the most interesting physics happen with regard to the generation of the solar magnetic field. So you have shear layers, you have differential rotation, you have some meridional motions. So if you have a bunch of field lines, due to all these motions, they will be intertwined, they will be twisted. And when these twisted flux ropes emerge from the solar surface, then they expand exponentially into the entire volume of the solar corona because the pressure drops very, very rapidly from a few meters in the convection zone to a few thousand kilometers pressure scale height in the solar corona. So there is an enormous change in pressure. It's basically magnetic field expanding from a dense region into vacuum. So people don't know much how these twisted flux ropes from the convection zone will evolve in the solar corona and how they will interact with the ambient solar wind. And the other problem is you need to have a stage in which you build some energy in the solar corona. The same way you cook pasta. If you put pasta in the pressure cooker, it doesn't cook right away. First you need to build pressure in the pressure cooker, and then when the pressure reaches some high value, then pasta will cook relatively fast. But what happens if you remove the lid? Don't try this at home. You will have pasta all over the ceiling. Well, that's basically what the CME is. So you have this slow building process in which you build energy into the solar corona in the form of some electric currents, volumetric electric currents around twisted magnetic field structures. And then you get the point when these twisted magnetic fields lose equilibrium, become very unstable, and they erupt. So there are 2 stages. There is the build-up stage, and then there is the triggering stage when the CME takes off. And once it takes off, it accelerates very rapidly in a very short time frame, minutes. And then it travels through space, drives a shock wave, and I'll talk about shock waves because shock waves accelerate charged particles, and that's what poses tremendous threat for satellites in Earth's vicinity, for electronics and so forth. And this is an illustration of one of our simulations. So we took a real event that took place on May 2nd, 1998, and we know that the event was produced in an active region in which one of the sunspots was rotating persistently over an extended period of time. And during this sunspot rotation, there were also episodes in which you cancel some magnetic flux. You push 2 opposite polarity magnetic field regions into contact, they reconnect. We didn't try to simulate the actual dynamics of the magnetic field because this is extremely challenging. But at this stage, we just simulated the general properties, namely the sunspot rotation and the cancellation of magnetic flux. And what you can see at the sun is, this is the actual magnetogram that we took from observations. The active region that produced the eruption is somewhere here. These are magnetic field lines, selected magnetic field lines, and you can see where the flux is. These are regions in which magnetic fields are intertwined. And the color along these field lines illustrates the current density. So you can tell what the current density is high. Probably it's the highest in the sun. But what is interesting is the flow speed. The flow speed is shown on this translucent surface that cuts through magnetic structure. And the regions in white resemble regions with speed greater than 1,000 kilometers per second. And you can see that the magnetic field lines that are part of the flux rope, they're moving the fastest. They're moving at a speed of 1,000 kilometers per second. And right here, where the transition between blue and red is, that's where the shock wave is. Basically, I visualize the velocity in such a way that you can see roughly where the position of the shock wave is. So what is interesting about this event is that we demonstrated you can form a shock wave very close to the sun, strong shock wave. And this is important if you want to study the production of energetic particles. The production of energetic particles has been under debate for an extended period of time. And there are a lot of unsolved problems at the moment. We know very little from observations about the evolution of shock waves close to the sun, how close to the sun they form, how strong they are. And we have also very little information about the level of turbulence in interplanetary space. We don't have satellites so close to the sun to measure the properties of turbulence. We know much better about the level of turbulences near the Earth from the cluster mission and from other missions, but not about the level of turbulence near the sun. In the future we'll have solar orbiter, we'll have solar core plus, so we can get an idea of what the level of turbulence is in the first 30 to 60 solar radii, but not in the first 2 to 3 solar radii. So if you want to form very high energy protons, 1 gigaelectron volt or higher, what you need is, you need to form a shock wave close to the sun, where the magnetic field, mean magnetic field is very, very high, because the maximum energy of protons depends on the local value of the magnetic field, the position of the shock wave. So that's why it's important to form shock wave relatively close to the sun, and then the maximum energy will also depend on the compression ratio of the shock wave. So now we have this model of a CME, we have some realistic evolution of the shock wave. What you have to do is take a kinetic equation and describe the acceleration of particles, and that kinetic equation depends on two important properties. One is the time evolution of the proton density, which determines basically the evolution of the compression ratio, and also we need to know something about the level of turbulence. And then you solve this kinetic equation, and what I'm showing here is distance from the sun in solar radii. One astronomical unit is somewhere here, and this is the energy of protons in megaelectron volt, kiloelectron volts. So 6 logarithmic scale, 6 corresponds to 1 gigaelectron volt. And this is basically the logarithm of the proton flux. And you can tell, when you inject some protons at a few kiloelectron volts, and when they arrive at the shock wave, they will be accelerated to some high energies. And when they accelerate to some high energies, their mean free path depends on the energy of they depend on the momentum of the particles. The higher the momentum, the larger the larger radius. So when these particles reach some large momentum, the larger radius becomes larger than the size of the turbulent eddies. And when you get to that point, then these particles are no longer accelerated, because the acceleration process goes by means of scattering of these particles back and forth across the shock between some turbulent eddies that are present upstream of the shock and downstream of the shock. And these turbulent eddies, they move towards each other because you have basically a shock wave moving through space. So if you have a particle bouncing back and forth between two converging mirrors, over time it will gain energy. But as I said, this process of gaining energy is not indefinite. It lasts as long as these particles can be scattered back and forth across the shock. But when the lava edges become so large that the particle no longer sees those turbulent edges, then it will escape. And it usually escapes in the direction where you have weaker field, when the level of turbulence is decreasing. So these particles will escape upstream and they will arrive in the Earth. So for this event, we simulated the production of solar protons at one astronomical unit, where we have actual observations by those 8 satellites. So we calculated what will be the fluxes of protons in different energy channels, compared with observations, and the agreement was very good, except for the timing. Our protons arrived 40 minutes after the actual protons. So you see, it's important to have this type of model that can give you agreement in something and disagreement in something else. Then you ask yourself the question, what did they do wrong? Well, apparently this time lag could be due to the fact that the shock wave in our simulation forms 40 minutes later than it actually formed on the real sun. Then you go back to the model and you make some changes in order to compensate for this time lag. So that's why it's important to be able to compare the fact observations and then go back to the model to provide some further validation. Another thing that we worked on was to study the structure of coronal mass ejections in interplanetary space. And we have a lot of satellites, such as ACE, we have Assoc, and they measure the properties of the solar wind in situ. What do they measure? Well, they measure the components of velocity, they measure the proton density, temperature, the components of the magnetic field, everything is beautiful. They can see the variations and so forth. And when you have a CME passing through a satellite, you'll see some dramatic changes. Most prominent changes will occur in the magnetic field. If you have a circular flux rod that goes to the satellite, at the front, the magnetic field will have one direction, and on the back it will have the exact opposite direction. So when the CME goes to the satellite, you see this smooth rotation of the north to south component of the magnetic field as the satellite measures the properties of the cloud. So people in the community came up with those models to reconstruct the structure of these so-called magnetic clouds. And they've been using those models on a routine basis. Basically, the idea is to reconstruct the three-dimensional structures of CMEs when they arrive to Earth. There is a problem. Here is where the problem is. We have a model, remember? We can put satellites anywhere in the computational domain. So in this case, we put the satellite at 15 solar radii. There is no real satellite at that distance from the sun yet. But we said, okay, let's see what this satellite, this artificial satellite will measure, and this is what it measures. Okay? This is the actual structure of the CME at 15 solar radii. So this is what the satellite will observe. Then we take these measurements from the satellite and we put them in one of those other community developed tools and we try to reconstruct the structure of the CME. And this is what we get. This is what you get from that other tool. Apparently, the actual simulation of the CME and the reconstructed structure of the CME will very different. And the picture doesn't change much if you put your satellite further away from the sun, say at 70 solar radii. This is the actual structure of the CME that you get from your simulation, and this is what you get from those reconstruction tools. And ask yourself the question, what did I do wrong? Is my model wrong? Well, not necessarily. We excluded the possibility that, suppose that you just have some CME, you know the two-dimensional structure. You don't ask yourself the question whether the model of the CME is right or wrong. The question is whether the structure of the CME that you get in your model is similar to the one that you get using a third model that's supposed to use some satellite, real satellite measurements to reconstruct the structure of the CME. And apparently, there is a great discrepancy. The discrepancy comes from the fact that those reconstruction codes that the community developed, they have a lot of assumptions. They assume that you have cylindrical symmetry, you need to specify some artificial boundary of your CME. May not be such a boundary. You see, the actual structure of the CME may look like a B shape, it may have a little dimple here. And that reconstruction tool doesn't allow that. It assumes that you have some cylindrical symmetry. And there are some other assumptions that are present in those tools. And the message that we send to the community is, people, go back to your tools and revise them. Allow those tools to have more relaxed assumptions about the cross-section shape of the CME, and also allow those field lines of the CME to not be just highly twisted, but also to have some amount of kink in them. When you make those assumptions, you come up with better agreement between the simulation, which gives you some ground truth, and those tools that people use on a routine basis. The advantage of these tools is that they run on the fly, they run very fast. This simulation takes a month to run. So apparently these are more advantageous to use because you can give some real-time interpretation of observations when they arrive. But the kind of simulations that we are doing, they give you a guide, of how you need to construct these models to give you a better representation of the reality. And I mentioned earlier on about filling data gaps. And this is an example of an observation of two interacting coronal mass ejections in space. And these are observations from the stereo satellites. You see that there was a data gap of almost 18 hours. And this data gap coincided with the time when two CMEs interacted in space. This interaction is possible because when two CMEs are launched from the exact same locations of the sun, the same active region. When the first CME goes out, it's like a snow plow machine. It evacuates all the solar wind material that is ahead of the CME. So what is left behind is a solar wind with much lower density. So when the second CME comes off, it will move much easier to what is left behind the first CME. So the second CME tends to catch up with the first one, and at some distance from the sun they interact. And when they do, you form this merged CME with much stronger shock wave that gives you a very bright signal in white light observations. And we used this numerical tool to simulate the interaction of the CMEs. And this interaction occurred exactly during the time when you had a data gap from the stereo satellites. So the simulations that we did basically helped you understand how the interaction occurred, and also how these two CMEs also interacted with a dense co-rotating stream that was present in the solar wind. So this is another advantage of simulation to help you understand missing observations. And this is one of the later versions of the work of Cooper Downs, my former graduate students, in which you compare stereo observations. These are in extreme ultraviolet, 171 angstroms, 195, 280, 284. And these are actual simulations, so you can see that the agreement is much better now. And this is for stereo B. And my student also developed the capability to simulate soft X-ray observations, also emission measure. So in order to come up to this really advanced stage of model which you can compare very precisely, these are not some random numbers, these are actual physical units, these are photons per second. Okay. We're not talking about some unknown units. He actually measures the actual photon count that comes in a given wavelength. And this took 3 years to develop. He actually did the work that could have taken 15 years if it was just very efficient. So he just took the most important physics that takes place in the solar corona, the heat conduction, the optical relative cooling. And the trickiest part is this coronal heating, the volumetric heating that takes place in the solar corona due to a number of processes. We know that there is solar convection, it shuffles the footpoints of the magnetic field, it launches some waves, these waves dissipate when they get to a certain height. We also know that there is some dissipation of current sheet, so there are a number of heating functions that are involved, and it's a very subtle play how you adjust these heating functions in order to get the best agreement between observations and simulations, and there are distinct regions on the sun. There is some important physics that takes place in active regions, and this physics is unimportant elsewhere on the sun. So it's very important to adjust the heating function so that, for example, the wave heating is dominant in these regions, and the heating due to dissipation of electric currents is dominant elsewhere on the sun. So it was a very challenging task. And once you develop this model, then you can study different type of phenomena that occur on the sun during coronal mass ejections. When coronal mass ejections take place, they are like supersonic jet that travels through the air. And you know what happens. There is a sonic boom. You have a shock wave that travels across the solar surface, it compresses solar plasma, and in regions where you have this compression, there will be higher emission, and this compression region moves across the solar surface. And you see these waves in extreme ultraviolet. We call them EUV waves. So people in the community speculated that these extreme ultraviolet waves are in fact the imprints of fast gravitosonic waves traveling across the solar surface. But you don't know for sure, because fast gravitosonic waves, they have density enhancements that are at a certain phase with the pressure enhancements and magnetic field enhancements. But that's not what you observe. You observe some emission measure in extreme ultraviolet, which could be due to something completely else, something completely different. It could be due to some heating. And remember, in the solar coronal you have very subtle balance between heating and cooling. So this could be some heating waves due to heat conduction and relative cooling that work on a very short time scale, and they could be completely independent from the evolution of the fast gravitosonic wave. So it was a big debate. Because remember, what you observe is not what doesn't always track the actual evolution of a given quantity such as density. So when you have a model like this, in which you can calculate the emission measure in extreme ultraviolet, then you can compare apples with apples. So here are the simulations, and he demonstrated quantitatively that indeed the evolution of the extreme ultraviolet wave is exactly the evolution of the fast gravitosonic wave, but not always. This is another example in which this is another event. This one is observed by SDO, and you can see the actual observations of these extreme ultraviolet waves in 3 different colors. And the colors are chosen such that red and yellow represent extreme ultraviolet at higher temperatures, and blue represents extreme ultraviolet at somewhat lower temperatures. And this is simulation. The timing is excellent, but these type of images are not very good for qualitative analysis. This type of images are better. What you're showing here is the latitude. You can see where the location of the center of the wave is, and this is time. When you have latitude time diagrams, you can measure much better what the speed of the wave is. You basically look at the slope of the front of the wave. So what my student did was compare with simulations with observations. Sometimes I'm getting confused between simulations and observations, but then you look at these spectacles and you can tell, this looks more real. So anyway, this is the evolution of the extreme ultraviolet wave, and this is the evolution of the physical ultraviolet wave. Agreement is excellent. But there is a second contribution, there is a second signal that you see in your extreme ultraviolet observations, and that's not related to the wave itself. That's related with the bulk motion of the CME itself. So you cannot always distinguish from observations which contribution comes from the wave and which contribution comes from the CME itself. But when you have a model, then you can make this distinction. And this is just to emphasize how important it is to have models if you want to interpret your observations. How much time do we have? I don't want to take too much time talking. I want to give you the opportunity to ask questions. So I'll conclude with the most recent work that we did that was published in Nature Physics, and this was basically the culmination of our efforts. So we have this model, which is great. But up until now, all our simulations start from the photosphere of the sun, and we impose some evolution of the magnetic field by hand. It's very artificial. Can we do better than this? We asked ourselves the question. If you want to understand the nature of CMEs, you need to start from the origin, and the origin is deep down in the convection field. From the perspective of modeling of CMEs, the most important quantity that you need to know is the motion electric field. Because this tells you how much magnetic flux emerges from the convection zone to the corona, to the photosphere. And that depends on the three components of the velocity and also the three components of the magnetic field. Once you know this electric field, you can determine the point of flux. So this is really important if you want to understand the evolution of the pointing flux from the sun and also the magnetic flux over the course, not just of a particular CME, but also over the course of the solar cycle, because we know that the large-scale field of the sun changes over a period of 11 years. It reverses completely. And you ask yourself the question, how does this happen? So, if you want to model CMEs very realistically, you need to prescribe this quantity as realistically as possible. And that's very, very difficult because from observations, you don't always have the three components of the magnetic field. As I said, you have for sure the radial component of the magnetic field. And for the horizontal component, there may be 180 degrees ambiguity in deriving this component, and that's extremely challenging to derive from observations nowadays. And even if you have the three components of the magnetic field, still you don't know much about the velocity. You can derive some components of the velocity in particular cases, but you don't have the actual physical components of the velocity. So that's why this quantity is extremely challenging. But once you know it, then you know exactly how energy is transported from the convection zone into the corona. And this is important for the build-up of energy that you need for the CME. One way to do it is to have this quantity realistically is to simulate the entire evolution of magnetic flux all the way from the convection zone to the solar corona. Then this quantity will be self-consistent at the visible surface of the sun, photosphere. But these type of simulations are extremely challenging because, as I said, the pressure scale height in the convection zone is only a few meters. When you go in the solar corona, we have tens of or hundreds of thousands of kilometers, so you have 8 orders of magnitude change in pressure. To simulate this in a global model is extremely challenging. It will require enormous computational resources, and a typical simulation will take more than a month. It will take a couple of months, up to a year to simulate. And apparently this is not practical if you want to do space weather forecasting, for example. You want to have a model that runs with real time or faster than real time, so it can predict when a CME will occur and what will be the consequences of a CME. So we found a compromise, and the compromise is, okay, there are great models about flux emergence from the convection zone. And we took the model developed by Arcontis et al. And Klaus Gausgraf from Copenhagen is also part of this team. So they developed a small Cartesian box model of emergence of a flux tube from the bottom of the convection zone to the photosphere. What we need is to have the information about the velocity and magnetic field at the photosphere. So we run this model and we save the physical information about the velocity, about the magnetic field at the surface of the sun, the photosphere. Once we have that, we have this quantity, the motion electric field, prescribed in a realistic, self-consistent manner. Then we take these results and we use them as time-dependent boundary conditions for the global model. So the global model will start from the photosphere. It will use these time-dependent boundary conditions that come from the Cartesian box simulation. But now, we don't have to simulate the entire region. We have two independent models that talk to each other, and basically that enables you to simulate the flux emerging process much faster by coupling the two models. The other advantage of having two models coupled in a way like this is you don't have just one region of the sun that emerges at a given time. There could be a number of active regions. This Cartesian box model you can scale. You can make it smaller, you can make it larger. You can change the orientation. You can scale the other physical quantities, so you can put it in other places on the sun that you resemble the appearance of other active regions on the sun. So you can use this Cartesian, you can reuse this Cartesian simulation in other locations on the sun in order to resemble the real sun. So this is another great advantage of having two models coupled in a way like this. And in this particular case, we assume that for the large-scale sun you have a simple dipole field. And what is shown here is what happens 20 minutes after flux begins to emerge in the solar corona. And these are magnetic field lines. Each color resembles different flux system. If you follow these magenta field lines, this is the large-scale dipole field of the sun. If you move just a little bit to the right, you see that field lines that are infinitely close at one end will become infinitely far away at the other end. You see the magenta field line connects over there, and this green field line connects right there. And if you follow the yellow field line, you see that it goes here, it goes around this surface, it enters inside, becomes highly twisted, and exits on the other side, and it connects right there. So each color here resembles magnetic field lines with different connectivities, and they resemble distinct flux systems. And this magenta surface is what separates the emerging magnetic field from the pre-existing field, and that's what we call separatrix layer. You have enormous gradients in the magnetic field along these separatrix layers. So because of the large gradient in the magnetic field, you build some electric currents along this surface. And as the emerging flux expands, as the new active region expands in volume, this surface will also expand in volume. And another interesting thing is there are two interesting points that are present in the solar corona as a result of this flux emergence, null points. And in fact, this continuous change in connectivity is due to the presence of these null points. And you have, in fact, reconnection taking place here. And that's why you have these sudden changes in connectivity. So we run this model for an extended period of time. We got a fast CME, but the most important thing is what is left near the sun when the flux emergence process ends. You would expect that flux rock will emerge in the solar corona the same way, in a self-similar fashion. But when we run the simulation, that's not what we got. If the flux rock emerges in a self-similar fashion in the solar corona, then you form a flux rock connecting this end with this end. But when you look at the actual simulation, there is no flux rock present here. Instead, you see two different flux rocks, one here and one over there, that are completely independent from the original flux rock that comes from the convection zone. This is very surprising result. Remember, we can reproduce various quantities. We can reproduce soft X-ray observations. And this is how the structure will look like in soft X-rays. And that's what you observe with an X-ray telescope. And many people, when they look at observations like this, they interpret them as being due to a kinked flux rock that starts from that end and ends right here. Sure, when you look at these observations, you can say that yes, this could be a single flux rock that connects from that end to that end. But when you look at the actual structure of the magnetic field, you see that these are two distinct flux rocks. One here and one there. And there are some field lines in between. And the soft X-ray emission is due to the fact that you have very hot channels of plasma along these flux rocks. Temperature here is about 20 to 30 million degrees, so planet will have soft X-ray emission coming from those regions. And when you have the capability to reproduce X-ray observations, you can measure the fluxes at different wavelengths, and you can calculate what will be the additional X-ray flux of the sun that will ultimately arrive to the Earth, heat up your upper atmosphere, slow down your satellites and so forth. So it's very important to have the capability to simulate the increased X-ray flux coming from the sun for space weather purposes. So this is the work that we published in Nature Physics in November of last year. You can send you a copy for those of you who are interested. But this is just to illustrate how you go around the problem of simulating the complete evolution of flux drop from the convection zone to the solar corona by having two separate models coupled to each other, which is a good intermediate solution if you want to do some kind of real-time simulation of CMEs, more realistic. And this is to conclude. Hopefully I managed to convince you that if you want to develop some realistic tools for studying observed phenomena, not just on the sun but elsewhere, you need to be able to reproduce actual observable quantities in your model. This means to use those observations as initial conditions, boundary conditions in the model, and when you have the capability to reproduce actual observations, then you can compare apples with apples, and you can go back to your model and make changes where necessary to get as good agreement as possible. And when you are able to provide direct comparison with observations, then you can provide improved interpretation of observations. You can validate the model, which is also very important task, and also fill data gap in present observations. Many people underestimate the importance of models, but believe me, they're much cheaper than to launch a satellite. But to have a model, you need to have observations. Model cannot exist alone. If they do, don't trust them. If they don't incorporate observations in one way or another, or you can say, oh, listen, I have this kind of twisted flux rope, and then you see this X-ray structure, yeah, this is a hand-waving argument. Show me in real photon numbers that what you actually simulate is what you observe, and then I'll believe you. And this is the argument that we've been having with observers for a long time. These are two different counts. People from the observing community say, this is the photon count, tell me if the magnetic field is strong there. And the best way to have two communities talk to each other the same language is compare apples with apples. And there used to be time, not too long ago, just 10 years ago, I'll give you just a little anecdote, when observers say, we don't see disconnected magnetic field in the heliosphere. Disconnected magnetic field means that these are field lines that are not connected to the sun at all. They have a V shape, they start from infinity, they go somewhere close to the sun, but they don't touch the sun and they go to infinity. And the observing community was telling us, those are artifacts, we don't see this. So we had to go back to our models, scratch our heads and try to get rid of all those disconnected field lines. But then came the stereo mission, and people saw white light observations that show you these field lines. And they were seeing dropouts in the electron density, which means that the electrons can no longer be reflected from the sun at two ends, and the only explanation will be that this field line is completely disconnected from the sun. So all of a sudden, this type of field lines appeared in observations, and then what are we supposed to do? We committed a crime before, we did our best to mask our crime, and now we have to go back and say, hey, listen, but we had this in the model, remember? You criticized us about it. So it's a long battle. And if you find something that observers don't see, take this with two sides. It could be a complete artifact, or it could be something that, due to the present limitations of observations, you just don't observe it. So take it with a grain of salt, and just send the right message to the community and tell them what are they supposed to do with their observations in order to make this particular phenomenon observable. And that's all I have to say. Thank you very much for your attention.